Okay, welcome back everybody. Thanks for waiting. Setting up live demos is always challenging. For everyone watching the live stream, we weren't able to get a screen share using Arch Linux. So what we're going to do is pass you the screen via a camera. So just let us know on the stream if you can't read the terminal window. And with that, I'm going to pass it over to Stefan to talk about the CTFE engine, and he's actually going to show us some live code. So take it away.
Can anyone hear me? Okay. Hello. First, you are not going to see code. I'm just going to talk, and then I'm going to show you some code. So, my name is Stefan, and at last year's DConf, I committed to rewriting the CTFE engine, and I told people I'm going to make it 10x faster. Well, it looks like I'm going to achieve that goal, and more actually, but the time the complete CTFE engine takes was a little bit underestimated. In the first email I said, Andrea, I said like, should be done in 3 weeks and we are ready to go. It suffices to say that now I have been working on it for like 9-10 months and it's still going on. There is a reason why this happened, and the reason is that code has weird complexity, especially in D, where you have a lot of complicated semantic constructs. It is very easy to get a simple example running, and if you want to go just a little bit higher, just a little bit more complicated, suddenly everything breaks down on you. It's like an exponential explosion of complexity. You just add a little drop into your bucket, and suddenly it has a great effect on the work you have to do. So with that, the first thing I'm going to show you is a live demo. I'm going to time source DMD, which is the freshly built DMD that's only available on my computer right now, because the auto tester has some weird issues and doesn't have the right version of the D runtime or something. And yeah, this is of what? Well, that's really a dry run takes 7 milliseconds. Anyway, let's run an actual file. It's called debug, and it is a file which I'm going to show you in a second after this completed. Let's wait. I hope my 2 GB of memory can handle this. It could totally be that the computer freezes up. Is it frozen? Shit! It really ran out of memory. I didn't expect that. Why? Because I'm running the duplicated display on the presenter mode there. And apparently that takes too much memory, even with that RAM enabled. Okay, let's pretend this would have completed, and it would have completed in I think this 14 seconds is all right. Let's see what this incredibly complicated, nasty code is that we try to run. Well, it does not look that complicated or nasty to me. Let's put this number down here. Maybe we can run it with DMD. Can always hope. Yeah, and it takes 1 second to count up to, I don't know what this number is, 100,000? I'm not good with numbers, probably. Anyway, when we run this with the switch BC-CTFE, we just see like 15x performance improvement, and we still have the same output, which is important. Actually, when you re-implement something, you want to get the same output. So that is the performance we get. I have another example, which may or may not work, depending on how much RAM it takes. Test big array should be fine. First, we are going to see how DMD performs. It's of course all DMD, but the old interpreter performs. It takes 3 seconds, and the new interpreter takes 0.4 seconds. And this is actually a really, really big breaking point, because if it takes longer than a second, then you feel like you have to wait. And if it takes less than 0.3 seconds, you feel like you don't have to wait. Let me demonstrate this. Let me make the arguments to that function a little more sane. And so you can see what I mean. Do this with a range? No, don't do the range. I can show you the range later. Let's use a little smaller argument. Let's test how long the normal compiler takes. It takes 0.4 seconds. But you see, I press enter, and there is a small, you can feel a small delay before you get the output. Now, let's use BC-CTFE. I press enter, and the output is there immediately. It feels like nothing has happened. And that is very important, because when you compile code a lot, this does not break your concentration. You can press enter and it's there. It's just there. You didn't have to actually think about, oh, I'm invoking the compiler and it does CTFE, and your thoughts don't have time to stray in 100 milliseconds. And if it's longer than that, you are going to be distracted a little bit, depending on your attention span. My attention span is really short, so I need a really fast compiler, which is why D is a great fit for me. Now I'm going to go into how I achieve that. And I'm guessing that I will need some fiddling with the slides, so bear with me. And there are not that many slides, so even if you can't see all of them, you haven't missed much. Actually open this. And it looks like the screen is so... Oh! It does show the whole slide, it seems like, because the screen clips at the exactly right moment. Okay, so what is CTFE? CTFE expands to, if you expand the abbreviation, compile time function evaluation or execution. We aren't really certain about this, but I would say evaluation, because CTFE is actually more than compile time function execution. It can evaluate arbitrary pure expressions, which is when you treat it as function execution, you attack it differently. And currently new CTFE cannot parse certain expressions because they aren't in the context of a function. And it's really nasty, because I took this acronym to mean compile time function execution, and some things cannot be done. So it's basically the ability to constant fold pure function calls. And it has many non-obvious applications, such as checking that certain enum members are defined in a certain relative orders to other enum members. What do I mean with it? Let me show you some code. Actually, this is from my BC interpreter. One of the backends of new CTFE is the interpretation thing, and it has like a number of instructions, like this add, sub, div, mul. Those binary instructions have a version which takes immediates. And it's very important that they're in the same order. You can see that they are in the same order. Here add, sub, div, mul, and you will see the same order in the immediates. And this is important for this emit arith instruction, where I just do, if I detect that I do it on an immediate, I add a fixed offset to it, and that allows me to do faster processing of code generation, because I want the code generator to be fast as hell, because it has to be to make this seamless experience of new CTFE possible. All right. I actually had a bug in there where I introduced a new opcode. Actually, it was a conditional set because I was inspired by Intel's instruction set, and in the end, it was a really bad idea. Don't add instructions just because you think the assembly language is going to be easier to program in, because at the end of the day you aren't going to write that much assembly, and the compiler has an easier job if your instruction set is not that convoluted and doesn't have that many special cases. And it's also much easier to do it in hardware, like probably the, what was his name again, the DHDL guy. Sorry, I'm terrible at names. Can you say your name? You're Lewis, right. Lewis will probably understand that implementing those instruction is really nasty. You require a ton of additional gates in your instruction decoder, and you probably want to break it down into microcode, and there are all these latency concerns to consider when you do chip design, so you want to keep your instruction set minimal. Usually there are some cache concerns, but I don't go into that right now.
Stefan, can you take a question from the chat?
Yes.
So Wobbles Grogan asks, will we be able to run debuggers at compile time? And also, compile time breakpoints would be cool. Smiley face.
Yeah, I actually posted this on the forums. I do have a plan to give you a debug interface for CTFE. Basically, DMD will open a socket, and you can, when you run CTFE, you can, it will wait if someone wants to connect to that socket, and then you can step through your CTFE code. This is what I'm planning to add in the next weeks when a few other problems are solved, such as short circuiting AND and short circuiting OR, which I tried to implement 5 months ago, and they still aren't working because they're evaluating some things twice because of the way the DMD's AST is structured. It can happen that one thing is the left-hand side of one thing and also the right-hand side of another thing, and when you naively visit the AST recursively, you will see those things show up twice, and you will evaluate them twice, and if those expressions have side effects, then your results are going to be really weird and you don't know what's going on, which is how I feel all the time. I think I have this, I made this forum post a while back. Let me just, where am I? Let me just quickly find it or not. Well, I'm probably not going to find it. I basically said, I am baffled, I am befuddled, I am confused, and I don't know what's going on. And this is how I feel all the time, because it's just such a hard problem. Anyway, when we do switch up something, we will introduce hideous bugs if the order changes. So I'm going to do that now. I'm going to switch up greater equals and greater than, which is one of the most hideous bugs you can have, because this bug will only manifest on one specific input, because the behavior changes only in one case. In all other cases, greater than and greater equals are the same. So it's really horrible if you want to exhaustively search for bugs. This is one you are not going to find easily. So when I now try to compile DMD, if I have enough memory to compile DMD, I don't know, then it's going to immediately give me an error, because it says, GT doesn't match to GE, you switched something up there. And this is what CTFE can do. And this is why CTFE is so great, because it can make you catch bugs you couldn't catch otherwise. This is also the reason why we need a faster CTFE engine, because this feature should be pushed to the nth level. CTFE allows you to build your own semantic checks into the compiler. It allows you to extend the error checking capabilities of the compiler. It's a use case which I hadn't in mind actually when I first did it, because I wanted to write trans compilers, but this turned out to be incredibly useful. Like the bug when I switched when I introduced a conditional set and I did not introduce a corresponding immediate conditional set, took me like 2 weeks to find, and now this will never happen again because it's statically asserts. Also, I had many bugs in the bytecode interpretation layer, because bytecode interpretation layer is hard. But I have now introduced something that allows me to catch those very soon. And this is actually the first time I'm going to show you what the BC-CTFE actually is. Not BC-CTFE, new CTFE. The project of my CTFE evaluator is new CTFE with a small new. It's written like this. New CTFE is the name of the project, and you have to write it exactly like this. Not with a capital N, with a lowercase n. It's very important because new CTFE is going to be the future, and I want to have it be recognized by everyone. Now, the way I implemented an IR to execute a function is normally you would specify some binary format and then interpret that format. But I found it was too inflexible. So I took something I borrowed from OpenGL. OpenGL has the ability to run code on a very diverse set of hardware. It runs on every graphics card you have, and it is not machine dependent to that card. And the way OpenGL achieves that is that it defines its interface through function calls. And when you define interface through function calls, you can interface to anything, and you can make the generator do anything. So this generator actually here it has a static assert that makes sure that this thing works. So this is very easy. We generate a temporary which will allocate space for it on the stack. Then we say we multiply this result. So what's the result? This is like a 3-address opcode, and you write it this way. You write it like inst. First comes the result, which is the BC value. BC value result. BC value LHS. BC value RHS. This is how those instructions are defined. So this is very easy to see that it actually says 2 LHS. The operation is times. So what you do is the result is 2 times 16, which is here in the comment as well. And here the same. We want to divide the result by 4 and store it in the result. So this is 32 divided by 4. And then we say sub 3, which is subtraction, and it subtracts one of the results. And then we return the value. And then we check here in the static assert that the value we return is indeed the 32-bit immediate value 7. Now, if I change this, you will see that the compile. Yeah, I have to fix the other bug first that I introduced. Sorry. It really was strange for my concept that I couldn't do a proper screen share, and also Yuri's talk filled my head with all kinds of thoughts, because it was like very inspiring. What was it that I switched? Greater than a gray equals. Okay. Now it should compile again, but it shouldn't. Because it will say that this static assert fails because it does not return 6, because it does indeed return 7. No, not in this file, it's in BC test. Static assert. There. Okay. Now it should compile. Okay, it starts linking when it says it can't allocate memory, then everything is fine. It compiled. Yeah, because I have those tests at compile time, that it compiled is enough for me. When it compiles, I know that it will work correctly semantically. And that's the real power of CTFE. It's like when you have a bug, you know it immediately without having to link the program and run your unit tests, which is going to take seconds of your time. And no, this is really important, because the usual attention span is like half a second. If it takes more than half a second, then you switch your mental context. Some do it more, some do it less, but there's a switch. And it is really important that if you hit an error, you want to know about it immediately. And also you can, because most people routinely compile their programs to make sure they at least compile. Now, just compiling the program can make sure that all the semantics of the bytecode interpreter are correct. And you can trust me, this saved me hours, because a bytecode interpreter is a complicated thing, and there are so many things that can go wrong, and when you can statically assert that everything works, it's great. this bytecode interpreter is very carefully written to be extremely efficient. Basically, it is completely inlineable, and I can show you this. Like even the DMD compiler does pick up most of the stuff that can be inlined. Let me show this. Oh god, how much time do I have left? I'm completely getting off track.
About 20 minutes.
Okay, I'm going to speed up, but first I want to show you that this thing is indeed completely inlineable. See? Oh, I do have to. I source. Yeah, of course, and I source DDMD, right? And of course the string import path. Res. Alright, this will have generated a file that lets you see the world how I see the world. And you're going to puke. This CG, right, yeah. This is what I see. So far so good, the enums are just converted to integers. I can live with that. It will show me actually the functions that were inlined, which is great to see. Yeah, oh god. Damn indentation, I can't show you anything because this terminal is too small. It will like, oh yeah, this is a bug in the header generator, but these inline functions here, they will expand to giant comma expressions and you have no idea what's going on. And yeah, it will show you that it will actually optimize many of those calls that would like store state and stuff. When it is correctly inlined, they just, here, this is where I emit a flag and I call a function that writes into the bytecode array. This will just be a direct write without a function call. So everything it does when you generate code is it basically writes 2 bytes directly. It doesn't even do a function call, which is very, very, very fast. Code generation is incredibly fast. Executing it is, as you saw, also not that slow. Oh yeah, this is a feature where you can like embed comments in the bytecode. This is something I wanted to use for the debugger, so you can embed the source lines in the bytecodes, so you can, when you step through it, you know what source line you're on, and you will be able to put breakpoints and stuff. You will also be able to inspect variables, also variables you never knew existed. Now I'm going to go down to the bottom of the file where, yeah, this is an expanded switch. It doesn't look that great. This is some Phobos thing to import some stuff, but it isn't too bad because it doesn't inline the function. If it would inline the function, it would span the whole page. Actually, we can see the Phobos implementation later on if we go over that switch. Oh yeah, this is how a for each looks. Beautiful, isn't it? When I saw this for the first time, I had no idea what was going on at all. And like put in all the switches, which is fine. This is all fine. And now we come to the bottom, which is going to show the horrible truth about templates. This is a number of old templates that are getting instantiated. And let me show you on which file are we currently. We are on line 225, and the thing has 20,000 lines. And all of those 20,000 lines is one different template instantiation and a bit of source code in those template instantiations. it goes on for quite a while. Maybe I should use page down. Yeah, and you can see all those wonderful Phobos templates in there. It's going to take a while to go through all of those because the terminal just updates at a certain speed. Oh yeah, that's really great. Can you see the? You probably can't. This is like a layered thing where it instantiates the same template over and over and over again. Yeah, all those templates are getting instantiated and sometimes executed at CTFE. There are still a few to go. Where are we? 37%. So this is why templates are slow, because there's so many of them and they produce so much source code. And the problem is you can't debug them at all. I have to say, C++ templates have the same problem, and they're worse. Actually, template bloat and time taken for templates in the compiler is way worse than CTFE could ever do. CTFE's impact is at most quadratic. Templates are anywhere from factorial to exponential, and probably even worse than exponential, but I don't know how you call that. Now, anyway, I think I still have 10 minutes, so let's go through those slides really quickly. I already gave you the demo, so okay. Two types of interpreters. They are AST interpreters, which take the AST and they produce an expression node or multiple expression nodes for every expression they visit, because otherwise it doesn't work recursively. It's a recursive AST visitor. Every time you hear the word recursion, you should be really scared. Recursion almost always means bad performance. And all AST interpreters have that problem fundamentally, and they will run out of call stack if you have 20,000 functions calling themselves. But the problem in DMD is that because of slices and concatenation, we actually have to copy some expression on every modification. And if we concatenate something onto it, the space requirement will grow exponentially. And this is why the simple for each loop over from 0 to 10,000 will require tons of memory and will run really slow, because it has to store the old value and get a new value. And that we never free memory doesn't make it better. It also doesn't make it worse, because those values are actually referenced. The garbage collector couldn't do any on it, because they're actually referenced, because we could need the old value in some specific cases when we are to deal with references and order of evaluation issues correctly. We actually have to keep a reference to the old value for everything. And this is actually something the CTFE interpreter does differently than runtime DMD. Order evaluation issues really hard. They are broken in new CTFE because new CTFE does not copy variables all the time. A byte interpreter generates immediate representation, some kind of bytecode, which are just bytes, which tell the interpreter what to do. I can just show you how this looks in the code. We have an interpret function. Takes a bunch of parameters to handle errors. It's not important. What it basically is a big switch which just does, okay, if we have an add, then add this value to our stack reference. If we have a sub, do this. If we do an end, do this. If we do an end 32, because it behaves differently than an end 64, cast it to a 32-bit value and do it. Blah, 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 blah. This just implements all the arithmetic expressions. There is no magic here. All interpreters look like this, which some variations. I did a lot to tune the interpreter, but it doesn't get any better than this. Like, all you can do is to, if you have some really extensive thing like doing a loop for a mem copy in an interpreter is out of the question, because every instruction will have at least a 10x overhead, and you really want to use an intrinsic for that. And this is how it looks. And this intrinsic here is actually also CTFE-able. Like I said, the whole bytecode interpreter runs at CTFE, so such that I can check the thing at CTFE. How the bytecode actually looks like, should probably get to the point in the slides. So bytecode interpreter requires you to generate another data structure, some kind of code you can execute, which could be also the final assembly you execute, which I will get to in the next slide. It can be slower than ST interpreters, because ST interpreters can make better use of caching, because they don't have to reference new values, but they're much easier to debug, because all the state is right in the IR, and you can like dump out what the IR does, which I would show you if I had a bigger screen, but I don't. And it is possible to convert to just-in-time compiler really easily if you do it right. If you only expose bytecode instructions that can be run on your native architecture, then you can just emit machine code instead of your own bytecode, and it will just run. You basically have a very fast interpreter, because the CPU vendor optimized its CPU to interpret that code. Yeah, this is the special case. If the bytecode equals the machine code, you have very fast JIT. You will generate very dumb assembly, but the dumbest assembly you can generate is still 10 to 15 times, sometimes 100 times faster than what your interpreter will give you. So it's a perfect trade-off for CTFE, because it's essentially zero cost in my model, because if I write bytes into an executable segment of memory, or if I write it into an array of bytecode, it's no difference. The operation is the same. It's just right. My design decisions for UCTFE were simplicity first. So we have no pointers to stack values or locals, because pointers to stack values are a giant pain in your buttocks, because they can change position depending on the stack pointer. And if you're in a recursive call, you have to like keep a second stack pointer or a context pointer, and stores some state on the heap, and you are going to end up with heap values anyway. So we don't have them in UCTFE. If you want to reference something, it goes on the heap. That's it. And every value that is not referenced by another function is what I call a true local, and can only be touched by your function, which actually enables some LLVM optimizations and the LLVM backend, but the optimizer takes like 15 milliseconds to run, and my slow bytecode interpreter is done 500 times before LLVM has even started up, because it has like some heavy setup in its data structures. I don't know why. It just basically just give me a zeroed memory block and then write the stuff in as it needs to, but apparently it has some initialization overhead to make some of the crazy optimizations they do faster. Yeah, every composite type, so structs and classes, if we support them in like 3 weeks or 5 months, it depends how you see it, is allocated on the heap and passed by a pointer, because that makes it very easy to implement method calls where you need to have this pointer. And like I said, you can't have pointers to stack values because it's really nasty to have that, and that's something that I disallowed in my very initial design, because I could already see that it would lead to giant thing. Slices, like dynamic arrays, which are slices, have the same ABI as static arrays, just that in static arrays you don't change the length, but the ABI is the same, so that it's very common in DMD that you cast static arrays to slices, and that is basically no op, because the ABI is the same. And generally I try to keep things very, very structured, even if it has a space overhead, just to keep the same structure everywhere, because APIs are a pain in the butt. Yeah, I actually had a bug where I had null pointer dereferences, because null is just another integer, it's just another memory address, and it would actually fetch the -1 byte in an array, which led to very interesting behavior. 5 minutes? Okay. Oh shit. Okay. The API for slices, we store the base first, because then we have less addressing computations to do. No, God. DIR. Okay. DIR, this is all the IR is. If you implement all those function calls, you have your own new CTFE backend. That's all you need. You need to store to the heap, you need to allocate memory on the heap, you need to compare stuff, you need to do the binary operations, you need to call stuff and to return stuff, you need conditional jumps, and you need to be able to allocate parameters and temporaries, and begin function at function marks the end of function body. I wanted to show you this code that I converted to IR by hand. It's a very simple power function, and I hope you can all see that it's correct for integer powers anyway, but you can't pass floating point stuff in there anyway. So this is the bytecode it expands to. It's really, really easy. You just say base is gen parameter, which is the same as saying int base. You have a second parameter, int pow, then you begin the function body, you make the result temporary, set it to 1, then you store a label for your while loop. If the power is 0, you go to the end where you return the stuff. Here's the end label. And if not, you subtract 1 from the power, you multiply the base by the result and store it in the result. And this end jump is needed to so we can fix up jump locations simply. This is why it's this strange end jump, begin jump. This is what we do when we already know where we want to jump to, which is here. and if this loop is finished, it will like run through here. We return the result and we end the function. Yeah, most time I spent on debugging actually because ABI issues are very complex, and this is a sentence I wanted to get in there. Definitely, out of 10 possible cases, you implement 3 correctly, 7 incorrectly, and you missed that you actually had 24 cases. Or probably not. You don't know. Bugs can hide the bugs, which can make invalid code seem valid in some circumstances because they happen to cancel each other in some circumstances, and in others they don't. And that is a recursive relationship. Bugs hiding bugs can hide bugs which hide bugs. And this should show you that debugging this low-level assembly form of code is really, really hard. And DMD's AST, which sometimes weird design decision, doesn't make it easier. Fun fact, 95% of new CTFE was written using GNU Nano without tab to spaces conversions, because I didn't get how to set up your .nano C, and the implementation of an and or is still buggy. It should be a simple thing, but still doesn't work. And concatenate equals is 30% slower in my interpreter because it like allocates everything every time you concatenate something onto it, and it actually has a factorial term in the space of text. And this is the last slide. So I'm done. Does anyone have any questions?
Hi, pretty impressive work. As you're merging this into the main compiler, have you thought much about how the two CTFE implementations can, say, coexist or something like that? Or what's the sort of migration strategy?
The migration strategy. Actually, a new CTFE is like a sidekick of a superhero. He's like over-eager, and he says, I take that job, I can handle it. And he like sprints to it and does the job really, really fast. And then it encounters a villain that it cannot beat, and it says, hey, superhero, Batman, I kinda messed up because Robin kinda sucks, and you handle it. And then the old interpreter steps in and does the work. So if we can do it fast, new CTFE will do it, and if new CTFE can't handle it, we will just let the old interpreter handle it, and that way we can make incremental progress without breaking the compiler. Yes. Any other questions?
Yeah, question here. I'm over here.
Where? Okay.
Do you think it's ever viable to use the existing code generator, maybe limited to safety?
No.
And okay. Why?
The problem is there are semantic dependencies in CTFE, and sometimes a function is not really ready for code generation. It should be in all cases if the world were fine, but the world isn't fine, and so there are issues. And the second more important issue is I don't understand the code generator, and I don't the code generator uses another IR. It uses another 3 IRs. And 3 IRs are difficult to traverse and it takes a lot of time to generate code. And it is just much, much easier if I have my nice linear bytecode, which I can convert to assembly immediately. It's just much, much faster, and the backend is hard to work with.
Our last question from Walter.
Well, it's more of a comment. The code generator is actually trivially obvious to the most casual observer.
Okay.
So thank you, Stefan. If anybody has further
Yeah,
questions, just
one announcement I wanted to make. After actually, I started to work on CTFE because I wanted to fix slow compile times. And back then, I didn't know that it was just the tip of the iceberg. CTFE is slow, but it still has like linear complexity. Templates have complexities I cannot describe with my limited mathematical grammar. And they need to be fixed much, much, much more. They take extreme times. And I think C++ has the same problem, by the way. All languages that support templates have the same problem, which is why Go doesn't support them, because they don't want these giant terms in their compile times. But I think I found a way around it, and hopefully next year I'm going to talk about my new template instantiation, which is going to be 100 times faster than what we have right now.
Thanks, Stefan. We'll take a quick 5-minute break, and then we'll be back for the last few talks of the day.